this video explain the reinforcement in the primary direction at the midspan. So if you have these supports, you have a reinforcement at the midspan. So the capacity of the 1 meter strip slab should be greater than the bending moment at this particular point. So in this, if I do the bending moment diagram, at the supports we have a negative moments and we have a positive moments, and at the supports we have this negative moment here as well. We have this negative moment here. So we found that at this particular point, at the mid one, where we have at mid spans, we found 22.7 kilonewton meter, and that was the positive bending moment. At the support, at first interior support, we found 25, which is negative 25 kilonewton per meter. So we need to provide the primary reinforcement for positive 22.7. Now the capacity factor phi equal to 0.85 is taken from table 2.2.2. I can show it to you in the standards. So if I go to the table 2.2.2, in here for bending, we have this 0.85. We are considering under reinforced 1 meter wide strip. So that is 0.85. That is called capacity reduction factors. Now we assume 1 meter wide strip, so it is convenient to assume 1 meter wide strip where we're going to find the reinforcement, and then based on the spacing that we're going to provide for 1 meters. Now this is exactly the same scenario as we are taking as a beam. So beam is 1 meter wide, and the depth of the beam that I think if you consider the depth of the beam that we calculated here, we calculated the depth of the slab. DS was 190 millimeters, and based on this cover and reinforcement, we found 159 millimeter was the small d. So in here we have same concept that we use in the beam. The concept was that we can have a stress in the concrete, so alpha 2 epsides, and the stress block has this depth A, and this is the effective depth, and these are the tension stress in the reinforcement. So if I just change it to the force, then the compression force in the concrete force, and the tension force in the steel bars, and this is a lever arm. Lever arm meaning that the distance from the compression force to the tension force is the lever arm. Now if I like to find the moment capacity for this 1 meter wide slab or strip with the small d value is 159, we calculated previously. So this is under pure bending. So in that case, we can take this moment at any point. So we take the moment at particular point where you have a compression force in the concrete. So the tension force in the steel times the lever arm will give us the moment. Now this force equal to stress times area. Okay, that equation here. So stress in the steel bar is yield stress Fy, and the area of the steels we need to find that, times this d minus a by 2, which is depth take away a by 2 will give us lever arm. Now it is challenging here, and it's time consuming to go through equilibrium and those scenario and find this lever arm and the neutral axis depths and so on. So there was a quick assumptions here that I like you to discuss with here, saying that okay, if you want to find the this lever arm for under reinforced beam, the neutral axis should be as high as possible in the sections. Okay, so the interior lever arm Z is not much smaller than the effective depth of the reinforcing steel. So your lever arm is much less than effective depth. So your lever arm should be less than this effective depth. So you can see this effective depth should be less than lever arm. So typically depth to the neutral axis dn may be taken as 0.15 to 0.13 times. That is the ductile failure. Although the same beam with the ratio may be as high, but this is 0.36 is very high. We don't consider this value. So in that case, you can say that dn equal to 0.15 to 0.3 d. So that is the That is the typically you will have the under reinforced beam with this in this range. So if you are looking for this dn value which is falls in 0.15 to 0.13, you can calculate this lever arm. So if you know this dn, this lever arm could be between 0.85 d. So it's a good assumptions here that these assumptions will give the moment capacity within plus or minus 10%. So in that case, if I do this lever arm which is 0.85 d, my calculations would be very simple, because 0.85 mu is this fsy which is 500 times as times 0.85 d greater than 22.7. Where this 22.7 comes from? I think we calculate this at the midspan, the moment at the midspan 22.7, and I'm working in the Newton millimeters, like to convert into the Newton and millimeters, so I multiply by 10 to the power 6. Depth, the effective depth is 159, so we calculated that effective depth 159 here. So that I substitute. If you simplify that, the ratio, the tensile reinforcement at this particular point is 395 millimeter square per meter. So that would be 1 meter wide strip at the midspan. You will provide the reinforcement 395 millimeter square per meter. In the next video, we're going to look at what is the reinforcement requirement here at the first interior support.